All right, so in this video, we are going to talk about sets. This is something you probably have learned a lot about already, so this is going to be pretty quick. The definition of a set is a collection of objects. It's about the least mathematical definition you're ever going to come up with. And these objects are called elements. All right, so if we have a set A and an element X, which is an element of A, then notationally we write that as X is an element of an A. If Y is not an element of A, we write that typical mathematical way, we just stick a line through it. Okay. A few more things. There is a set with no elements. We call this the empty set. We write it like that. Okay. How do we describe a set? There are two ways. All right, first is the roster notation. We simply write out the elements. All right, A could be the set that contains 2, 4, smiley face, diamond. The set that contains 1, 6, and alpha, and square. All right, so note, here a set is also an element. All right, it's possible for sets to be elements. All right, so this roster method is fine if you have a finite set. It's also fine if your set has some sort of pattern to it. For instance, the even the even natural numbers, 2, 4, 6, 8, 10, and you can kind of keep on going like that. All right, or if you wanted it to be finite, even natural numbers less than 50, 48, 50. All right, and your reader can naturally fill in the blanks. But if you have something a little bit more complicated, we need to use what's called set builder notation. All right, and this is a way of defining a set that basically says it's all the elements that satisfy some condition. All right, so we have a set. It's all the elements of X in some sort of universal set. Say the integers or the real numbers or some big set, such that X satisfies some condition. All right, so note, this vertical bar means such that. All right, we could also use colons. All right, sometimes a colon is a much better thing to use than a vertical bar, especially when the condition here involves absolute values. All right, then you can get mixed up with your vertical bars. All right, so this is how we describe sets. We can either use the roster notation or we can use set builder notation. More often than not, we're going to use set builder notation. Also, in set builder notation, this is one of the few times where it's okay to use the symbols for there exists and for all. Okay? This is one of those few times where you really want to be brief in how you're describing things. So if for exists or for all or there exists is part of the condition that X needs to satisfy, then this is a good time for that because you want it to all fit in one line if possible. All right, this next bit is really important. Subsets. All right, one of the main things we're going to be doing in this class is talking about subset inclusion and how to prove that one set is a subset of another. All right, so given sets A and B, we say A is a subset of B if for all elements X of A, X is also an element of B. Okay? Notationally, we write this as A, this funky kind of sideways cup thing, B. All right, and you notice this sort of looks like less than or equal to, right? And that's on purpose. All right, you can kind of think of A as being a smaller set than B. But of course, there's some key differences. Not every set is a subset of every other set. But the line down here is really important because it is possible to be a proper subset. If A doesn't equal B. All right, because of course B is a subset of itself. You will end up proving that. But if A does not equal B, but is a subset, then it's called a proper subset. And the way we write that is without the equal sign. Okay? Or without that underbar. So what's another way of writing this definition? Well, we can actually write it as an if-then statement, and this makes it really nice for proving things because we know how to prove if-then statements. So we can say that A is a subset of B is another way of stating that is that if X is an element of A, then X is an element of B. And this right here, this is beautiful. This is an if-then statement. All right, we know how to do if-then statements. So think about this when you're trying to prove that two things are subsets of each other. You start with a hypothesis, you end up proving the conclusion. You could turn this into a contrapositive. You could prove this by contradiction. We know how to deal with if-then statements. All right, and finally we have combining sets. All right, set operations, just like we have logical operations. So we have things like the union, A union B. So X is in the union if X is in A, or X is in B. All right, we have the intersection. All right, so X is in the intersection of two sets if X is in A and X is in B. All right, we have set difference, basically subtraction. And that's A slash B. So X is going to be in the set difference of the two if X is in A and X is not in B. All right, so you take A and you subtract off all the parts of B. All right, and finally we have the complement. AC. So X is going to be in the complement of a set if X is not in the set itself. All right, a few more definitions and then we should be done. So if the intersection of A and B is the empty set, we say A and B are disjoint. And finally, A is equal to B if A is a subset of B and B is a subset of A. This is really important. This is how we show that two sets are equal to each other. All right, we don't examine every single element because usually they have an infinite number of elements and that's not possible. Instead, what we do is we show set inclusion in both ways. All right, and finally we have special sets called the power sets. All right, and the power set so let's say we are given a set S. The power set of S, which we denote by script P of S, is the set of all subsets of S. So it's a set containing all of the subsets. The elements of the power set are the subsets of S. All right? So this is a really prime example of a case where you have a set containing sets, which then contain elements. All right, so this is all the basics that we need. In class, we are going to work through some exercises, and we're going to work through a lot of proofs to understand really how do we work with sets.